Thanks. Let's begin with a word of prayer. Dear Heavenly Father, we thank you for this day. Thank you for the break. Just completed. Just pray be with us today. Help us to, again, Lord, glorify you in what we do. In your name I pray, Lord Jesus. Amen. Well, today is one of those days where we are going to get further ahead of the other section. We are soon coming to the point where you guys are going to get to skip a day. So we're going to be a full hour ahead of them by the end of today, so yeah. I'm not sure when we'll skip, but sometime. All right, so let me just talk about your homework to the start of class here a little bit. Do you guys have any particular questions? Let me talk about the ones I have on the board already. How about that? So I don't recreate the wheel. See here. Let's talk about I'm sorry, some of these are essentially complete solutions. Let's start about 22. Actually, before I talk about 22, let's talk about the big picture of convergence, divergence tests. Like, it's not exactly a flow chart. It's, I don't know, a web of conspiracies. I'm not sure what you want to call it, but I decided to think about it from starting here and then working my way out. My goal is to decide whether the series converges or diverges. I used to draw it as a flow chart because it'd be like, do this, then this, then this, then this. But I decided that that's not really the right picture of how we think about things. It's really more like some sort of massively parallel process. Because to start with, you don't think about one thing, you think about a bunch of things all at once. You think about the kth term test. Is it geometric? Is it a p-series? Is it alternating? Does it appear to be telescoping? I really think about all of these things right at the start, because those are just pattern recognition, right? You just look at it and go, oh, that looks like the stuff is to a k power. That's probably geometric, right? Or it's just 1 over, some k equals 1 to infinity of 1 over k to the 5th. Well, that's p equals 5, so I'm done, So the first thing is just recognition of, like, is it something basic, right? Then when I get past that, if it doesn't just jump out at me what the thing is, then my next line of thinking is I try to intuitively understand what it is for large k. So, like, for example, this one, root k to the 7th over k to the 18th plus 2, basically the k to the 7th and the k to the 18th are dominant. And they say, to a good approximation, this is 1 over k to the 11th. It's essentially a p equals 11 series with some noise. And so then I've got choices. I can either try to just I'm going to compare to a p equals 11 series for this one. And I can either go limit comparison or I can go basic comparison. And which one you do just kind of depends on what you see. I mean, if you see the necessary inequality, then you can do direct comparison or basic comparison. If you don't, then you can try the limit comparison, which is kind of more, you divide two things and you do algebra, right? So it's less inequality based. Limit comparison's a little bit safer in that regard because it's mostly based on algebra, not as much based on your understanding of inequalities, right? But you should be working to improve your understanding of inequalities, right? That's one of our goals. I guess there's two main goals in calculus too, which is to help you learn algebra and inequalities. You're like, wasn't that the point of algebra? Yeah, but there's always more to learn. So that's in the red, compared to a p-series. The other kind of comparison that can happen though is more. This is a little bit more weird example. Like, I maybe put one of these on a test. In a given year, there's a chance I wouldn't test on this, but some years I might. And that's comparison to something that has a nice integral test, something like some n equals 1 to infinity and e to the minus n squared, right? I know that the integral of x e to the minus x squared basically is x times e to the minus x squared, and I know that the exponential to the minus x squared wins. It goes to 0 more fast than, or quicker if you like, than x. And so I can kind of think through this back of the envelope calculation in my mind and know that converges. So if I had something like this given to me, I might be tempted to compare it to that, which I could then use the integral test to prove converges. You see, this is kind of second order logic though, right? It's not the first thing I think about, but it's there if other things fail. Now, excuse me. I always have, when I think about, I guess another thing I might add to this is like, I guess I don't add that there though. I don't know. I mean, the question is divergence, right? Like, how do you judge divergence? Well, I think when you check into this, intuitively for a large K, what does it look like? If you get something that doesn't go to 0, that's where you learn it's divergent, right? Now there are series which don't go to 0 and yet are not obviously so, right? You've experienced this. There's some rather complicated formulas that can hide a divergence, hide the kth term test's application somewhat malevolently. Okay, so telescoping, well, that's kind of like if you got something like 1 over k times, 1 over k plus 1 times 1 over k plus 2, something like that. You can do partial fractions. You're going to get a difference of things. It's going to be telescoping. Telescoping, you kind of have to learn by example. But any telescoping example, if it's from rational functions, is going to be comparable to like a p equals 2 or p equals 3 series or whatever, right? So you're going to expect that it converges from your intuition. You know what I'm talking about? Like, just to be less opaque here, if I got something like 1 over k times 1 over k plus 3 or something like whatever, something like that. Well, if I run this guy through my intuition meter, I go, that's 1 over k squared. So it converges, right? So I actually could do direct comparison to p equals 2 series, or I could do limit comparison to p equals 2 and show it converges, right? But then what I wouldn't get is the value to which it converges. So that's kind of another bit of advice. If you're asked to find the sum of the series, well, what are your options? It might be a geometric thing. It might be telescoping, right? And then the other case, of course, is the more sneaky stuff, like it's actually the value of a known Maclaurin series evaluated at a point. That's the harder thing to see. But that's kind of a separate. I'm trying to just focus on convergence and divergence here, right? So I guess if you're just interested in convergence or divergence, this probably doesn't matter as much because usually you can, if it's one of the rational ones, you can solve these by just direct comparison or limit comparison to p equals appropriate series. I guess on the other hand, if it's something like inverse tangent of n minus inverse tangent of n plus 1, you're actually going to have to calculate the nth partial sum and take the limit as n goes to infinity to show it converges. All right. Beyond that, right, beyond these basic things, you've got the root test and the ratio test, right? Those are our last best hope for understanding stuff. I guess we'll pass this, right? There's stuff like direct comparison or limit comparison to stuff that you can do with the root test or ratio test. I mean, there are worse things beyond. Beyond this is the Dirichlet test, which I don't think is in your book. What's that?
It even sounds harder to pronounce.
Dirichlet, yeah. Yeah. There was a problem that the faculty here couldn't solve a few years ago. Like, how do you show this converges or diverges? I don't understand this problem, blah, 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 blah. And I took it home to my wife, and she looked at it, and she's like, seriously? They can't solve this? Like, no. She's like, this is just Dirichlet test, blah, 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 and she told me. I'm like, okay. But my wife she had calculus in Hong Kong in high school, and then she had a course in mathematical physics, where they actually, did math. Anyway, my wife is irrelevant. Oh, I'm sorry. Hope she's not watching this. Don't worry, she's too busy to watch this. Our secret is safe here. Any questions about my general jibber jabber over there? The other thing that has been advised, is that a word? I don't think. Some good advice would be to see page 596. This has some nice advice about just looking at the formula. Is it ratio? Is it root test? This one here, is ratio test. I mean, you see factorial, you think ratio. I think ratio anyway. And so you got to calculate the quotient of ak plus 1 over a sub k for this one. So I do k plus 1 factorial squared divided by 2k plus 1 factorial. And then I have to divide by k factorial squared divided by 2k factorial, which is this. So the thing I'm using here, the big idea, two big ideas really. K factorial is equal to k plus 1 times k factorial, right? The other big idea in this calculation is that 2k plus 2 factorial is 2k plus 2 times 2k plus 1 times 2k factorial, right? I've talked about this before, but you need to internalize this idea about how to work with factorials, right? The reason to do that, of course, is that once you do that, you can cancel the k factorial squared, and then later you cancel the 2k factorial, and you're just left with this quotient of quadratics. If you divide the top and the bottom by k squared, it gets you to something that's 1 over a fourth, which is less than 1. So by ratio test, the given series converges. I'm sorry, I seem to have done one of your homework problems. I hope you can forgive me. Yep. There's a quiz tomorrow. So I hope you've done your homework. If you have, the quiz shouldn't be too bad.
On the test in which we'll be tested on these, can there please be not as many problems as usual, especially since you can start down one path and find out that the path leads you nowhere and start over all over again?
Well, doing math is much like practicing the piano. You can only play the piece at full speed once you do enough problems. And the same for calculation. So I'm not going to, I mean, this is the course it's always been. I give tests essentially the same as I have in previous years. To do otherwise wouldn't be fair to the past or the future. So I can't really cede to your demand there. I mean, I understand what you're saying, but you know, you got to learn to work. You have to ask yourself, you know, as I'm working the homework, how am I going to understand this question without taking a half hour for it, right? So that's part of what I'm talking. Never what? I'm not sure what you mean by that, but.
You're saying that like you're not going to change it because it was different in the past.
I think if you look at Calculus 2 tests over a wide variety of universities, you'll find something somewhat similar. So, I mean, is my teaching optimal? Am I not changing things? Well, obviously I'm changing things. Am I changing for the better? I don't know. I question this every day. But what was I going to show you guys? Oh, are there any other? See, do I have any other homework problems up here? I've got the estimation question. Here's example 6. Let's talk about example 6 from section 12.6 for a second. The question is to estimate e to the 0.2 to 3 decimal places, right? The question is how many terms do you need to take in the nth Taylor polynomial evaluated at 0.2 to make that happen? And in order to answer this question, we need a tool, which we don't yet have. And so like earlier today, I was trying to solve, not that it matters to you guys, but I was trying to solve the error estimation questions in 12.6, right? So I hope everybody can, you guys should all be able to do the problems before the error estimation, you guys should have just fine, right? But the error estimation questions are rather mysterious, unless you like cheated and read the book. I'm being facetious, of course. Yes, if you read the book, it shouldn't have been that hard, but, well, that's my problem. I haven't read the book enough recently, And so I forgot that in section 12.6, and this is my own fault because what? We haven't been doing proofs in here, right? So I was just showing you how to calculate things, and I forgot that in order to do the problems in 12.6, not the starting problems, right? But exercises 17 through 20 or 21 through 24, these are all based on using Lagrange's formula for the remainder. And I was trying to solve those with alternating series estimation theorem, which is sometimes relevant, sometimes not. So, yes, to basically any of the exercises from 17 through 20, you want to do kind of the same idea as example 6 in the text, all right? So here's example 6. To calculate e to the 0.2 using a Taylor polynomial, well, the nth Taylor polynomial looks like this when you evaluate it at 0.2, right? Because remember, we worked out e to the x is x to the k over k factorial, k equals 0 to infinity. So if I truncate this series, this power series at n, that gives me the nth Taylor polynomial. If I plug in x equals to 0.2, I get this, right? Lagrange's formula for the remainder says that the nth remainder is actually equal to the nth derivative evaluated at some point c divided by n plus 1 factorial times x to the n, right? Well, I will explain this more. I'm going to actually prove this for you guys today, or try to. And anyway, the point is, well, that's because the nth derivative of e to the x is just e to the x, so I plug in 0.2. X is equal to 0.2, so I get 0.2 to the n plus 1 factorial. You can replace e with 3 because e is 2.71. This is not a profound step, okay? And then 0.2 is 1 over 5, right? So that's 1 over 5 to the n plus 1. And you either want to solve that, I mean, I could say equals, but perhaps it would be more appropriate to say less than. Ow! Yowzers. Why do we say less than or equal to 0.05? This is for what? To get certainty for first 3 decimal places. So like I could, if I had 1.3784, I could be sure that these guys were correct if I had an error less than at most 0.0005. That's just as close as, I mean, if you had more than that, you could have a rounding error in the last thing.
So the 5 in the last digit is just something that's normal to use.
That's what the book advocates. Personally, I worry. So I would make it personally, I would make it 0.001.
Yeah, when I did the formula,
I'm just greedy.
when I did the formula, I was wondering why it wasn't 0.001.
Again, if you think about how we round the 4th digit and the fact that this isn't, it's not that it's equal to 0.005, it's actually less than 0.005. So the most it could be would be like 0.4999, right? So that means that the last digit is, the 3rd digit is certain if you start thinking through it. I'm a little bit worried about how thinking through it, so I want to make it 0.001, but I'm also trying to follow the book. The book says 0.005, so I'm like, oh, fine, I can live with 0.005. Now, the larger question is, where on earth does Lagrange's formula for the remainder come from? All right, and I want to explain that to you guys, but I also want to focus on your homework for the start of class. So I'm going to have to come back and talk about Lagrange's formula for the remainder after I've fielded any homework questions you guys have for today. Huh. Interesting. I can actually talk now. Yes?
How did you get from the 3 over 5 to n plus 1 times n plus 1 factorial is less than or equal to 0.02?
That's from the question asks us to estimate what n you need to. I'm not done yet, by the way, this example. You still have to solve that inequality to find the n to make it so. How do you do that? To finish the thought, you actually have to solve this inequality. Yeah, this is that helps us to figure out which n we need in order to make that approximation within point, to make the approximation good to 3 decimal places. But again, how do you actually solve such an inequality? We just start plugging in values until it's so. So for example, 6, he mentions, but I took this as as a point to emphasize that we can get away with not proving things for so long, but eventually it will catch up with us, and that was this morning for me. So he says that the least integer to satisfy this inequality is 3. You can try n equals to 1, n equals to 2, n equals to 3. This one fail, yay. Pragmatically speaking, as a generic piece of advice, when you're trying to solve one of these inequalities, what you want to do is try one, see how far you are off, and then if you're not getting closer to what you want fast, skip a few ahead until you've gone past the point you want, and then you go back. So you don't have to go 1, 2, 3, 4. You can go 1, 2, oh, this is going too slow, 20, oh, that's way too small, 10, oh, that's closer, 15. You kind of like, when you're guessing, guess smart. So for number 22 in the homework, you're faced with a function that you happen to know the nth derivative is bounded by 3, right? And you're asked to find what n what n do you need? Sorry, guys. What n do you need? The question is to find n such that the error in f of 2 minus the nth Taylor polynomial 2 is less than. Well, the reason I'm putting this here is because it says to 3. We need 3 decimal places. I'm certain in the PN2 approximation, all right? So you have to solve this inequality for problem 22 and 12.6, but if you look at Lagrange's formula for the remainder, we know that there exists some c such that the nth derivative divided by n plus 1 times x to the n is actually the remainder. That is less than or equal to 3. Now, the reason I can put 3 there is you're given in this problem the nth derivative is bounded by 3. And then, well, you have x equals to 2. So you just got to solve this inequality. My very generous hint to you is start at 8. Not that 8 is the answer, but you might as well start at 8. That would be a mean hint if I knew the answer was 50, but I don't. The answer is not 50. All right, modulo the proof of Lagrange's formula with the remainder. I think that's about all I have to say about 12.6 error problems. Do you guys have other questions? What's your question, Mr. Anderson? 12.5, number what? Number 22. And which one did you have a question about, Mr. On? 12.6, 14, 12.5, 22. 12.5, number 14, was it? Say again? Number 22 of what? 12.5, number 22, and what was the other one? All right. 22, is that minus 1 to the k divided by k plus 1, sum k equals 0 to infinity? No? Okay, cool. So let's see, yours is to find the nth Taylor polynomial for Pn, f of x equals to natural log 1 minus x. You just leave that there, and you're supposed to find Pn of x. Is that right? Okay. come back to that in a second. 12.5. Sum k equals whatever, minus 1 to the k squared over 2 to the k, right? Now, the whole thing I just erased is kind of no fun. It's no fun when you're just working in the alternating series estimation test section. So it's like, oh, it's alternating. Well, of course it's alternating. It's in the alternating series section, right? But if you can imagine yourself outside the box and just facing this problem on the open field of battle, you would recognize it as alternating because it's got this stupid minus 1 to the k in it, right? All right. So we have to recognize that this is an alternating series, right? What's the b sub k? Right? Which is clearly positive. Is it decreasing? Well, I think there's something to worry about. Can we show it's decreasing? So we need to show what to show it's decreasing? We need to show that b sub k plus 1 decreasing, yeah, less than b sub k, or equal to. So let's see here. Let's see if we can just do that by direct argument. Maybe we can do it by direct argument. I don't know. We'll try. B sub k is equal to b sub k plus 1. It's k plus 1 quantity squared divided by 2 to the k plus 1. Which is what? Is less than or equal to what? So I can do k squared. Well, no, I can't do that. I mean, I guess I can do k plus 1. I don't know. The bottom line is here, I'm not enjoying this. Let's do it a different way. No. How do you show something is decreasing? I mean, if you can see through that, good. If any of you could see through it and you didn't help me out just now, you're bad people. But how about this? If we let f of x equal to x squared divided by 2 to the x, all I need to do is to show that the derivative of f is negative beyond some point, and then through the connection between continuous functions and the corresponding sequences, I'll have that the sequence is decreasing, right? Now that is something we can handle. What's f prime of x? Heh 2x times what? Times 2 to the x minus what? Right? So this is what? This is 1 over 2 to the x times what? Times 2x minus x squared ln of 2, which is what? 1 over 2 to the x times x times 2 minus x ln of 2.
Maybe 1 over 4x instead of 2x?
Yeah.
Or, oh, you just cancel out all the 2x's.
Correct.
It's the 2x.
Right. So we made this reduction. This and this cancels with that basically, right? Okay, so I can think about the sign chart for f prime. to gain an understanding of where is it increasing and where is it decreasing. Where are zeros? Well, there's a 0 at 0, obviously. And there's also a 0 wherever this is 0. So critical points give me, equal to 0 gives me critical points. For critical numbers, if you like. So we got what? 2 minus x ln 2 equals to 0. What's the solution to that? Two over ln 2, right? Whatever that is, what is that? Ah, okay. Very good. So you can check it's positive in here and it's negative over here. So basically we have that k squared divided by 2 to the k is decreasing for k greater than or equal to 3. A lot of the other examples we've looked at before this point, we haven't needed to make this analysis. Like another example in your homework, another one in the homework here in 12.5 was what? It was the one I wanted to talk about. Where's that thing? I don't know, there's tons of examples. Like 16, minus 1 to the k over k times k plus 1. Is it square root? Square root, yeah. By the way, without the so here, I have b sub k is equal to 1 over the square root of k times k plus 1. And I don't think you need to make a further argument. In my opinion, and it's just my opinion, so you can take it or leave it, I guess, but probably should pay attention. I do grade your test or whatever. Ignoring that silly thing. This is positive. What I'm trying to tell you is this is positive and decreasing. I am willing to accept that you can see that this is positive and decreasing without further commentary. It's clear to me from that formula it's positive and decreasing. I think it's also clear to you. It should be clear to you it's positive and decreasing, right? Because you've got 1 over something. As that something gets larger, it gets smaller, it's decreasing, right? Why wasn't it obvious here is because I've got 2 things which are getting larger, so there's an ambiguity there that I have to address, right? Heuristically, you think there's hope, right? Because we kind of know 2 to the k beats k squared, right? Exponentials beats polynomial. But I'd kind of like to see some detail if there's that kind of ambiguity. Yeah? Unless, of course, I'm just asking you to ascertain whether it converges or diverges without proof, right? There's 2 kinds of questions I can ask you. Find if the series converges or diverges versus show it converges or diverges, right? There's always that. Yep.
You will ask us about whether it converges absolutely too, right?
Yeah, this one will not. This is a conditionally convergent one, this one. Because intuitively speaking, this is essentially the, for large k, this is like the square root of k squared, which is like 1 over k. So this is just a twisted harmonic series. It's an alternating because of the minus 1. If you strip off the minus 1 to the k, though, you're back to essentially the alternating series. Pretty sure that this is a conditionally convergent example. But yeah, that's also something we need to think about. Conditional versus absolute convergence. Anyway, I just wanted to show you why I wanted to bring this up because I want you to understand that we don't always have to do this stuff. It's just in the case that the b sub k isn't clearly decreasing, then it requires some further analysis. And the purist would say that this isn't a complete solution because I should also prove that it's positive and decreasing. I just, I get tired of proving things that are obvious when if I can avoid proving something that's obvious, I'm going to give you the freedom to not do so as well. All right, so let me get back to Mr. On's question then, and this was a question more about this one.
We're done with 32?
We're done with 22, yeah. Oh, well, I guess we're not quite done. You're right. Fine, fair enough. I'm halfway through. So I've shown that it's decreasing, right? Thus, note k squared over 2 to the k, extending k to be continuous by L'Hopital's rule, infinity over infinity gives me what? 2k over natural log of 2 times 2 to the k, right? And then another L'Hopital, infinity over infinity, 2 over ln of 2 squared times 2 to the k, which goes to 0, right? So that shows that b sub k goes to 0. Again, I think some detail is required because it's not immediately obvious that b sub k goes to 0. Excuse me. Up here, I think it's also clear that this goes to 0, right? As k goes to infinity. I don't think you need to do further L'Hopital. I mean, obviously you don't need to do L'Hopital. It's clearly going to 0, right? So the same problem that doesn't really require much commentary about why it's decreasing or why it's positive is probably, conversely, the other problem that does require such analysis because the formula is just more subtle. All right, so let's regroup here. What do we have? We have that b sub k is positive. We have it's decreasing. We have its limit 0. Therefore, the sum minus 1 to the k times k squared divided by 2 to the k from k equals 1 to infinity converges by what? The alternating series test. Who cares? Oh, you care because it's the homework, yeah. Fine. Well, I just checked for conditional convergence, right? Well, I guess I don't know if it's conditionally convergent until I know that the absolute value series diverges. So to check for absolute convergence, I have to take the absolute value of the series and analyze the convergence or divergence of that. So for part A, which I'll golly, for part A I'll do over here in red. What's that? K equals 1 to infinity. Sorry. I have to analyze this. That's the absolute value of the series, term by term. In other words, it's the sum of this guy, right? We have to analyze, does this converge or diverge? What's that? I haven't done that. I haven't done that. I have the series with the plus or minus converges by the alternating series test. There's no plus or minus here, though. It's a different series. I can't use alternating series test to say boo about the absolute convergence. Absolute convergence is another thing. Now, intuitively speaking, it's going to be convergent because 2 to the k is like way bigger. It's essentially, well, the 2 to the k is going to win. And how to say this? I mean, I don't know. Yeah, I think ratio test is probably a good idea here. You can show converges by ratio test. Yes, correct. You are correct, sir. So Mr. On's point is that I'm wasting your time by showing you why it converges directly in terms of alternating series. I'm fitting words in. I know you're not being mean to me. It's fine. I'm sorry. I need to get to know you guys better so I can pick more effectively on you. So the point that you were making is that we have proved the other day that absolutely convergent implies convergent, right? So Testy series for absolute convergence or conditional convergence. If the absolute value of the series converges, it's not conditionally convergent, because conditionally convergent means that the absolute value of the series does not converge, and yet the series converges. So if in part A, if you test the absolute value of the series and you get that it diverges, you're not done. You then have to check, does the series itself converge? If the series itself converges while the absolute value of the series does not converge, then it's conditionally convergent. Like this one, number 16, if you calculate the absolute value of this, right, you've got and you can show that this diverges by comparison to p equals to 1. You could use limit comparison probably, or I don't know. Maybe you could even use direct comparison, basic comparison. I don't know, whatever. Anyway, you can show that that series diverges, and yet this one converges. Therefore, number 16 is an example of a conditionally convergent one. If it's conditionally convergent, it is not absolutely convergent, okay? But I do think you're right that once I show that this is absolutely convergent by the ratio test, I don't actually need to go through all this. Man, fair enough. So I guess a more interesting question for me to ask in view of that is just, does this converge? Now, if you're smart, I guess you can avoid this stuff, right, by just checking absolute convergence and using absolute convergence implies convergence. And so you can get around some of this calculus I was doing. So you're going to have to make me work harder. I guess you guys know too much. If you knew less, it'd be easier for me to force you to think about this calculus in an exam question. But I am not really trying to pigeonhole you into making a certain argument most of the time. I just want you to be able to solve standard problems like in your homework. Questions? Other questions, I should say. Yep. 12.5, number 26. Now, this is just the alternating harmonic series. In disguise, we're looking at the sum cosine pi k over k. K equals 1 to infinity, right? This is conditionally convergent. If you look at the all right, so what is cosine of pi k first of all? Cosine of pi minus 1, right? Cosine of 2 pi 1. Cosine of 3 pi minus 1. Cosine of 4 pi 1. Are you bored yet? Okay, so cosine of pi k is just minus 1 to the k. So first of all, let's understand its true nature. This is nothing more than the alternating harmonic series, which is, by the way, our quintessential example of a conditionally convergent series. But just to go through the argument, for part A, you have what? 1 over k. K equals 1 to infinity that's equal to, right, like this. The absolute value of the series is actually the harmonic series that diverges, right? by the p equals 1 series, by p equals 1 test, or whatever you want to call it. It is the p equals 1 series, right? We know that that diverges. We applied the integral test back in the day to prove that, right? Now part B, if you look at the series itself, right, minus 1 to the k divided by k, you've got b sub k equals to 1 over k, so you can apply the alternating series test to obtain, this is a sketch, convergence. Therefore, it's conditionally convergent, right? This is not a complete solution. This is an outline of a solution. The complete solution will include comments like b sub k is positive, decreasing, and has limit 0, right? But I'm tired of writing. Oh, thank you. I'd rather work on number 14. That's my happy place anyway. Let's see here. All right, so we're looking at f of x equal to the natural log of 1 minus x. And you're supposed to find Pn of x. There are two ways to do this problem. So what are the two ways you could do this? Three ways maybe. The first way, well, you could use our work in the previous class, right? I already worked out the natural log of 1 plus u was equal to the sum k equals 1 to infinity of, like, I think it was, or k equals 0 to infinity of, what was it, minus 1 to the k divided by k, I think, times x to the, well, u to the k. I think that's what I had. Right, it's just like 1 minus u plus u squared over 2 minus u cubed over 3 and so forth, right? Okay, but yeah, I'm about to say, I hope that I'm wrong because I have division by 0, right? Thank you. Is that? Oh, u to the k plus 1 too? Oh, okay, thank you. I forget. And you see, that's why that's not a great solution, is because it requires us to actually remember, you know, what we did the other day. Am I right now? How did we work that out? We worked it out by differentiating, applying the geometric series, then integrating to get back to the series again, right? So you could do the same for this, right? You could do what? You could go, okay, so this goes to df dx is equal to minus 1 over 1 minus x, which is the sum k equals 0 to infinity of minus 1 times x to the k, right? And then integrate to get f of x is equal to a constant plus the sum k equals 0 to infinity minus 1 x to the k plus 1 divided by k plus 1. Of course, you know that this is also equal to the natural log of 1 minus x, and that will, again, we'll make c equals to 0 because it has to match up, you know, x equals to 0, natural log of 1 equals 0. That forces the constant to be 0. Bam. F natural log of 1 minus x is equal to the sum k equals 0 to infinity minus 1 minus 1 over k plus 1 x to the k plus 1, right? Right, yeah, I did something wrong here. Where? Why? Why would I do that? What's my thought process going from here to here? I mean, I might have an error, I just don't see it yet. My thought process here is a is equal to minus 1 and r is equal to x. The difference in the problem we worked in the other classes, we had 1 plus x downstairs. So like 1 over 1 plus x, right? I have to look at as 1 over 1 minus x in order to compare with like a over 1 minus r. R is equal to minus x, and this, you know, the thing we did before, the difference. And that's what created the minus 1 to the k in the formula. In this other formula, that's where the minus 1 to the k came from. So, I didn't complete the thought with the u. What would be the completion of that thought? Is you just do what? Set u equal to what? Sorry, my brain's skipping a little bit. This is a side comment, really. And then you could just set u equals to minus x, right? And that would be one way. You could piggyback off yesterday's example, set u equals to minus x, plug it in. You should get the same thing we're about to get. Right? The other way would be to walk the steps we walked yesterday, right? Differentiate, geometric, integrate. That gives us back this series, which is that, right? And then the third way, which is the first way you guys told me, which was to just do what? Follow the section. Stop doing all this stuff from later in the chapter, right? This is after all 12.6. We don't know this stuff yet, right? Quote unquote, don't know it in the book. So the other way to do it, of course, would be just by direct application of Taylor's formulas, right? So to do that, we do what? F of x is what? Natural log of 1 minus x. F prime of x is what? Okay, f prime prime. Minus 1 times minus 1 times minus 1 for 1 minus x squared. The third derivative, minus 2 times, let's just say that this is minus 1 over. So we have minus 2 times minus 1 times minus 1. There's always an extra minus, right? Let's see, I've missed one, haven't I? There's the minus from the start. There's a minus 2. I forgot something here. No, I guess it's just these two. Just those two. Oh, but there's another one, isn't there? Let me... Sorry, guys. Let me... Do you guys agree with the previous one? The 1 minus 1 is there from the start. The other one is from the chain rule. The other one is from just differentiation of the reciprocal function. Like inside function, reciprocal function. So this one, let me just try to talk you through, try to explain where the minuses are coming from, all right? So first of all, there's just pull the minus out, right? There it is. Next, my thought is that that's minus 1 times minus 2, 1 over x minus 1, x minus 1. 1 minus x. Goodness gracious. It doesn't matter here, but it matters later. It matters when it's odd. Yeah? So let me not get in a bad habit. So 1 minus x, right? And then times what? Chain rule says times the derivative of the inside function, which is 1 minus x. That's why I have the 3 minuses. And I'm sorry, this is a what? We decrease the power when we differentiate by 1, so the 2 becomes a 3. So that's why I wrote minus 1 times minus 1 times minus 2, or whatever order you want to write there. All right. Are we good? What's the fourth derivative? Let me just clean this up. This is what? So the fourth derivative gives me what? Minus 2 times minus 3 times minus 1 over 1 minus x to the what? To the fourth. Okay, so by now hopefully you can see a pattern. The nth derivative evaluated at x is what? It is n minus 1 factorial. There's a net minus, and I divide by 1 minus x to the n power. Therefore, if I calculate the nth derivative at 0 divided by n factorial, that's 1 over n factorial times minus n minus 1 parentheses factorial divided by, 1 to the n. Very exciting. 1 to the n. Hardly worth writing, but I'm plugging in 0 there, right? If we were working somewhere other than 0, this would be more exciting. That 1 to the n wouldn't be something. It would be something to the n, but it's not because we're plugging in 0, because we're calculating the nth Taylor polynomial centered at 0, because this is section 12.6, and that's what it talks about. Now, this is n minus 1 divided by n factorial, right? Which is what? N factorial is equal to n times n minus 1 factorial, right? So in view of that, these reduce to just give me minus 1 over what? N. So therefore, and I should really be using a k here. Let me fix that. I'm sorry, guys. Let me just rewrite it. In other words, the kth derivative at 0 divided by k factorial. Because he uses n in a different context in this problem, so I'm getting myself into trouble here if I'm not careful. I mean, right, just change the letter to k, because we want to talk about the nth. What's the nth Taylor polynomial? Remember, Pn of x is by definition, and we're centering it at 0. That's clear from the context in this section. K equals 0 to n. The kth derivative evaluated at 0 divided by k factorial times x to the k. But that is exactly equal to the sum k equals to 0 to n of, what is that? Well, that's minus 1 over k times x to the k. And there you go. Of course, that is exactly what I found over here, right? Oh, can't do math. Let's see, what have I done? This observation is good for n greater than or equal to 1, right? What happens, so I should say, plus what? What is f of 0? Zero? Oh, okay, thank you. All right.